Good afternoon. Before I get started, I've got a couple notes for you while they're setting up power and all. Stop by the business hall located in Bayside A and B during the day for the welcome reception at 1730 through 1900 tonight. And then we have the Black Hat Arsenal, and it's in the Palm Foyer on level 3. And then you should also join us for the Pony Awards in Mandalay Bay, B, C, and D at 1800. There, 1830. If you can put your cell phones on vibrate, we'd appreciate that. As far as that's concerned, welcome to South Seas A, B, and C. We have HEIST going on, and I will turn it over to these guys. Thank you.
Okay, good afternoon, everyone. I am Matti van Oef.
And I'm Tom van Goetem. And we're both researchers at the University of Leuven, so we're from Belgium. And today we will be talking about HEIST, or HTTP encrypted information can be stolen through TCP windows. So in this presentation, we will first start off with some technical background to make sure that everyone is on the same level. So we will look at the same origin policy. Then I will briefly discuss how compression-based attacks work. Then Matti will give a brief introduction to SSL, TLS, and TCP. So these are the main building blocks of what becomes HEIST. So then we will discuss the details of this attack. And of course, this wouldn't be a proper Black Hat presentation if it didn't contain a nice demonstration. And in the end of the talk, we will briefly touch upon the countermeasures that can be used to prevent this attack. So before I go into what the same origin policy exactly means, let's look at this very simple example. So on your left, you have Mr. Sniffles, which is your average web user. And Mr. Sniffles goes to his bank, so bunnybank.com, and he wants to access his vault. So in order to do so, he will send a GET request to bunnybank.com. This GET request will contain the cookies of Mr. Sniffles. And when bunnybank.com receives this GET request, it will associate the cookies with the identity of Mr. Sniffles, and will return the vault to Mr. Sniffles. Of course, in the web, there are other websites besides bunnybank.com. So Mr. Sniffles also goes to other websites on the World Wide Web, so to look at funny videos, to share his pictures, some more naughty websites, and of course there's also websites that are either owned by attackers or that are infiltrated by attackers. And any of these websites can send JavaScript to the browser of Mr. Sniffles. And this JavaScript can initiate the exact same request as in the previous slide. So it can send the same GET request to vault, also with the cookies of Mr. Sniffles. Now, because bunnybank receives this request, it doesn't know that this request was initiated by a different website, so a cross-origin website. So it will simply return the vault or the contents of the vault to Mr. Sniffles as it did in the previous slide. But of course, there's the same origin policy. So the same origin policy basically says that any website from a third party is unable to read out the contents of the cross-origin response, in this case, the vault. I should also mention that because bunnybank.com is offered over HTTPS, any man-in-the-middle attacker will also not be able to access the contents of the vault. And what's also important to note here is that not only the contents of the vault should remain hidden, but also the size of the vault. So whether the vault is large or whether it's small. Because knowing the contents of the size of the vault might already leak some information about Mr. Sniffles to the attacker. So in a nutshell, this is how the same origin policy works. So now I will move on to the second part of the technical background, namely the compression-based attacks. But before I go into the attacks, I will briefly mention how compression works. So a lot of websites on the internet are served with gzip compression. And it works as follows. So on your left, you have the uncompressed resource. So you requested /vault and then some vault secret. And it totals to 51 bytes. So when this resource gets compressed, it will try to look for strings that occur twice or 3 times or more. So in this case, the string vault, so V-A-U-L-T, occurs twice. So the second occurrence of this string will be replaced with a back reference, which is much smaller than the complete string, than repeating the complete string. So in this case, 5 bytes disappear because we have the vault, which is 5 bytes. They disappear and they're replaced with a single byte in this case, so a back reference to the string. So as a result, the compressed resource now has a size of 47 bytes. Now, as an attacker interested in the vault secret, he will do something like this. So he will send out multiple requests. So he will start with /vault secret equals A, and then A, B, C, and so on. So with A, you can see that again the vault string is compressed with a back reference, but also the secret and equal sign is compressed with a back reference. But because the character following the equal sign, the vault secret there is a C, and the attacker tried to guess an A, that doesn't get included in the back reference. So the resulting resource size there is 50 bytes, but as we can see on the right, when the attacker guesses the character C, you can see that the C is included as part of the back reference. So this means that the response size is now 1 byte less, so 49 bytes. So the attacker can look at if the attacker manages to look at the response sizes, you can see that 49 bytes on the right-hand side is smaller than the 50 bytes on the left-hand side. So that means that the character C was the correct guess. And basically you can keep on repeating this and try to brute force the secret character by character. So then he guesses CA, which compresses to 49 bytes, and CB, which is 50 bytes. So because CA is smaller, he knows that that is a correct guess. So that basically sums up how compression-based attacks work. So these attacks are actually not very new. So they've been known since 2002, when someone at an academic conference mentioned that by combining plain text information of the attacker's choice with some secret information, and the complete document is compressed, this allows for the leakage of the plain text secret. But these attacks became much more popular and well known when the crime and breach attack were introduced, so in 2012 and 2013. So crime exploits the compression on the SSL level, whereas breach exploits it at the HTTP level, so with gzip compression, as I just shown.
Okay, so the last part of the background knowledge that we need in order to understand the HEIST attack is how SSL on TLS works at a low level. So I'm going to quickly explain this using an example. So let's say we again have our friend here, Mr. Sniffles. He wants to request the contents of the vault, and to do that he's going to send an HTTPS request to the server, so to the vault resource. So this is accomplished by first establishing a TCP handshake. You probably all know these details. Since the bank uses HTTPS, we also first initiate an SSL handshake, so we have an SSL connection. Once this secure connection has been established, the browser will send an HTTP request, and you will encrypt it using using SSL. Now generally this request is rather small, so it fits into 1 or 2 TCP packets. And once this request has reached the server is going to reply with the contents of the vault, which in this case we're going to assume that the vault fits in 29 TCP packets. So how is TCP going to send this content back to Mr. Sniffles? Well, it's not going to send everything at once because that might overload the network. Instead, we have the TCP slow start algorithm. And what essentially happens is that initially it will send the first 10 TCP packets to Mr. Sniffles, to our client. The reason we only send 10 packets is because the initial congestion window on most systems equals 10. And the initial congestion window, also called TCP window, basically states how many packets an endpoint can send without waiting for them to be acknowledged. So in this case, we can send the initial 10 packets here. They are sent at almost exactly the same time. And then we have to wait 1 round trip until these packets are acknowledged. So we are receiving 10 acknowledgements. And the interesting part here that for every acknowledgement that is received here, the server will increase its TCP window by 1. So previously the TCP window was 10. Now we are receiving 10 acknowledgements, so we have 10 plus 10. Our TCP window is now 20. And now the server can send the remaining contents of the vault. So we already sent 10 packets here, meaning we have 19 packets left. And because the TCP window has now increased in size, we can send all these 19 packets at once. And this completes the response to the server. So you can already notice here that between receiving this first window and the second window, we have 1 whole round trip time between that. And we're going to abuse that later on, but Tom is going to explain that now.
Let's go into the details of HEIST. So HEIST is basically a set of techniques and methods that allow an attacker to measure the size of a response that as it was sent over the network purely in the browser. And by having these techniques, we can then perform compression-based attacks such as crime and breach. So I will now go into the details of how this works. So first, we exploit 2 browser side channels. So the first one is with the fetch API, which if you don't know it, is very related to XML XHR requests. So we can basically send out requests to any endpoint that we choose. So here we use the fetch method to bunnybank.com/vault, and we give it 2 options. So the mode is set to no course because we don't want to use the cross-origin resource sharing mechanism, and we set the credentials option to include because we want to include the cookies of Mr. Sniffles. So this method will return a promise, and if you don't know what a promise is, it's basically a callback that gets executed as soon as this promise resolves. The promise will resolve as soon as the first byte of the response is downloaded by the browser. So this allows us to measure the point in time at which point the first byte of the response was downloaded. Then we have another side channel So there we use the resource timing API, which allows us to measure when the last byte of the response was downloaded. So now we know the time when the first byte of the response was downloaded by the browser and the last byte was downloaded. HEIST consists of several steps, and in the first step we will try to determine or leverage these side channels to determine whether a certain response fits into a single TCP window or whether it requires multiple ones. And for that we'll take a look at the timeline of what things get triggered when a small resource is sent to the client. So with small I mean smaller than a single TCP window. So we first call the fetch method. This will initiate this TCP handshake and SSL handshake. And after that, the browser can send out the GET request to the bunnybank.com, for instance. When receiving this GET request, the bunnybank.com will answer with a response, and because it fits in a single TCP window, it will send all the TCP packets in a burst to the client. And a bit later, so a round trip time after the GET request was sent, the first byte of this response will be received by the client. So we mark this as T1. So this coincides when the promise of the fetch method resolves. And a very minimal time after that, the complete response is in, because all the TCP packets were sent in a single burst. This time is very minimal. Now, when we compare this with sending a resource that takes up 2 TCP windows, so we see that we have a different timeline. So everything up until T1 is exactly the same, but after that, the browser or the operating system of the client will need to acknowledge receiving the first packets. So it will send out the acknowledgements, and only after the acknowledgements have been received by the server, then it can send out the second TCP window. And then it takes more time for the complete response to be received by the client. So if we compare the difference between T2 and T1 between the first, for a small resource compared to a large resource, we can see that the difference is significantly higher for a large resource, and it's actually a round-trip time extra for a larger resource that required multiple TCP windows. Of course, this only gives us a very limited amount of information, so we know whether a response is smaller or larger to the single TCP window, which is approximately 14 kilobytes. So that doesn't give that much information. So as an attacker, we're much more interested in knowing the exact size of the response. And for that, we will use some technique with reflected content. So reflected content basically means that content of the request, so the attacker sends out the request so he can determine what content gets sent in this request, and this content is echoed back in the response. And using this technique, he will try to determine the size of the actual resource size, which at this point is unknown to him. So in the graph, it's the green part that he will try to determine. So first he starts off with a reflected content of X bytes, and he notices that when he reflects X bytes, then the response takes up two TCP windows. So we have the initial congestion window and then some additional data in the second TCP window. So what he then does is he divides the number of bytes that get reflected by 2. So then he again measures whether it fits in a single TCP window or whether multiple were required. And in this case, it fitted in a single TCP window. So then he will have to increase the number of bytes that are reflected. So he increases it by x over 4. And basically he keeps on doing this. So after log n steps, he can find the tipping point. So the tipping point here is y bytes. So it basically means the number of bytes that are required to completely fill up the initial TCP window. So if he would add a single byte extra, it would take up 2 TCP windows.
Okay, so Tom explained us how we could determine the exact size of a response, so a resource that fitted into a single TCP window, which is roughly around 14 kilobytes. I'm now going to explain how we can apply a very similar technique to determine the exact size of a large response. Now, what do I mean with a large response? With a large response, I mean a reply, so a resource that does not fit in the initial TCP window. Like I mentioned, the TCP window is around 10 TCP packets, so it's a packet that is, so we are talking about responses here that are bigger than 14 kilobytes in size. Now, how are we going to do this? Well, we're going to rely on 2 elements. The first one is, like I explained previously, that the TCP window at an endpoint grows as packets are being acknowledged, and we can use this to increase the TCP window at the server side. So I'm going to explain this again using an illustration. Let's say we again have Mr. Sniffles here, who has loaded some malicious JavaScript, and the attacker can now make requests under his name. So here we again want to recover the content of the vault, and more specifically the size of the vault. So in this example it's 19 TCP packets. And the first thing that we're going to do is we're going to increase the congestion window, so the TCP window at the server side. And to do this, we're going to request an unrelated resource on the website, in this case foo. It has to be loaded on the same website, so the same TCP connection will be used. But anyway, the browser or the JavaScript code will request this resource. The server will reply with this resource to the client. In this case, it's 10 TCP packets. And these TCP packets are acknowledged by the victim in this case. And once these acknowledgements arrive at the server, for every acknowledgement, the congestion window, so the TCP window, is increased by 1, meaning we now have a TCP window of 20 at the server side. So right after the browser, so the computer basically of Mr. Sniffles sends these acknowledgements, we're also going to request the contents of the vault. And when this request arrives at the server, the congestion window is still 20 in size, meaning now this reply, which is 19 TCP packets, can all be sent at once to our client here. While normally if we didn't include the TCP window at the server, these 19 TCP packets would be divided in 2 windows. But by enlarging the TCP window, by first requesting an unrelated resource, we can make sure that this reply here fits in a single TCP window. And now we can apply exactly the same technique as Tom just explained. We can use reflected content to increase the reply here, and when we can determine when we reach this tipping point where we need 2 TCP windows to send back the reply. So the clue is that we have a large resource here which can be sent in a single window. So the final part of our HEIST techniques is that we can abuse HTTP2 to improve our applicability of our attacks. So first, a very quick introduction to HTTP2. As the name clearly implies, it's a replacement for the older HTTP1 protocol. Now, HTTP2 does not change the semantics of HTTP, so you still have your ordinary post on GET requests, you still have headers on cookies that are sent along, you still have the division between the header and the body of a response, and so on. The main difference is that HTTP2 encodes the responses on a different way at the network level. And the most important change here is that when you're using HTTP2, only a single TCP connection will be used to send all requests. Because with the older HTTP1 standard, if you were loading a website, your browser would make up to 6 parallel requests to download all images from this website. But with HTTP2, only a single TCP connection is used. However, this single TCP connection can be used to send multiple parallel requests to the server. And we can abuse this way how HTTP works to improve our attacks, namely by exploiting HTTP. And how we're going to do that, I'm going to explain in the next slide. But what we are able to achieve is that we can now determine the exact size of a response without requiring that there is reflected content inside the specific response, so inside this resource. So that's the first advantage that HTTP2 brings us. The second sort of related advantage is that, let's say you have a resource where there is some kind of secret in it, and you want to apply the breach attack to extract the secret, but there is only a very small amount of reflected content inside this resource. Because there is only a very small amount of reflected resource, it means we might be able to apply breach. However, this small amount of resource is not enough to really fill in the TCP windows. But even though we can't use this resource itself to find this tipping point, we can abuse features of HTTP2 to still execute the breach attack, even though the reflected content is very small. So let me illustrate how this works, again using an example. Let's say we again have our victim here on our server, and we want to determine the size of the vault. In this example, it's going to be 6 TCP packets. And we have an unrelated resource which is also hosted on the same website, which we call Reflect. And here in my example, I'm going to assume that if we load this resource, it will be sent using 3 TCP windows. So how does the attack work? Well, we're first going to send an HTTP2 request to the Reflect resource, and immediately after that, we're also going to send so almost a parallel HTTP2 request to the Vault resource. So like I mentioned, these 2 requests happen in the same TCP connection. Now, when this request of the Reflect resource arrives at the server is going to reply with this resource, so that's 3 TCP packets that are already sent here. And immediately after that, it's going to receive the request for the vault and is going to reply with the 6 TCP packets of the vault. So in total, we have 3 plus 6 TCP packets, so we have 9 TCP packets that are sent almost at once. Also, an important remark here is that even though we are using HTTP2, we can still use the same side channels in the browsers to determine when the first byte of a resource was received and when the last byte of a resource was received. So we can still use these browser side channels to determine whether this Reflect, and in particular, whether this Vault resource was received in a single TCP window or not. Okay, so we can now apply a very similar technique to find the tipping point. So let's say in this case we reflect 5 TCP packets in our Reflect resource. We again have the same requests here, but now the server will first reply with the Reflect resource, which is 5 TCP packets. Then it will try to send the 6 TCP packets of the Vault, but it can only send 5 TCP packets because then the TCP window is already full, and it has to wait 1 full round trip to receive the acknowledgements before it can send the remaining content of the Vault. And using our browser side channel, we can clearly see this timing difference purely in JavaScript. So to summarize, we have our HEIST attack, which is able to expect the contents of our vault using reflected content and using this browser side channel. We can also abuse features of HTTP2 to improve the applicability of our attack. And now I'm also going to demonstrate the attack live, so hopefully that will work. So basically we're going to inspect the contents of the vault here using the breach attack. So let's do that. So let's switch to my VMware here. Okay. So let's say we are the victim. We are Mr. Snuffles the rabbit. We're going to visit our bank, bunnybank.com. As you can see, it's a very professional and obviously very secure banking website. So we're going to log in as Mr. Sniffles using his password. And there we go. We are now logged into the website, so we can see our balance, we can see recent transactions, and so on. The most interesting part here is that we can perform transactions to other people. So we can fill in the destination address, we can fill in how many characters we want to send. Now, as an attacker, it would be very interesting if we could perform transactions under the name of the victim, so under the name of Mr. Sniffles the rabbit. However, this is not that trivial because if we look at the source code, we can see that this form here, which is going to basically send the request of this transaction to the server, we have a CSRF token here that the attacker needs to know. So we can't easily apply a CSRF attack. We have to first obtain the CSRF token and then we can apply the attack. So let's assume our victim is going to visit some other website, let's say the New York Times. He's going to read the news. Okay, let me zoom a bit. Great. Okay, so we have our website here. So in this case, we assumed that there is an advertisement banner on the website. And we all know that these third-party advertising companies, they are not always that secure. So let's say that in this example, our attacker manages to attack this third-party advertising company, and he is able to deliver malicious JavaScript code to the victim through this banner. So in the background now, our HEIST JavaScript code is ready to run. So I'm going to generate some background traffic so we can see that the attack still clearly works even though there is some background traffic. And then I'm going to execute our HEIST attack. So this is running. So now our attack is running. Now, of course, in a real attack, this pop-up window is not going to be there because then it would be obvious that the victim knows an attack is going on. But this is just to illustrate how our attack will work in practice. So the first thing that our attack does is it's going to try to find the tipping point where if you would send one more request, the resource would no longer fit into a single TCP window. And once we have found this tipping point, we can start to execute a variant of the breach attack. So now it's trying to guess the character. It's a bit slower than when we tried this ourselves, so I'm going to try to reload this. This is not working perfectly.
Live demonstrations.
Yeah, this is a live demonstration, so hopefully it will now better work this time.
So as Matti showed, it's possible to use HEIST to launch compression-based attacks, such as breach and crime, for instance. So for breach, virtually every website is using gzip compression. And if you have gzip compression combined with a resource that returns reflected content in the response and contains a secret, it's possible to reveal the secret using the breach attack. And next to the breach attack, there's also other types of attacks that can be used with HEIST. So there's the size exposing attacks. So by simply looking at the size of the responses, it's possible to reveal or uncover demographic information about the victim by abusing certain popular social networks. If the victim would be using some online health platform, it's also possible to reveal the victim's health conditions and so on. So it's basically based on what the functionalities that are offered by the websites that determine which types of attacks can be performed. So in our research, we looked at many large websites, and actually we had trouble finding websites that are not vulnerable to either some compression-based attack or a size exposing attack. So given that these attacks are pretty severe, it's good to take a look at what can be done to prevent these attacks. So as you can see, there are a lot of possibilities to prevent the attacks, but unfortunately most of the defenses are either infeasible, inadequate or incomplete, with a single exception, which is disabling third-party cookies. So if the request from Mr. Sniffles to bunnybang.com does not include the cookie of Mr. Sniffles, then bunnybang.com cannot associate the request with the profile of Mr. Sniffles, so no sensitive information will be sent out to, sent out in the response. So by default, all major web browsers enable third-party cookies, unfortunately. However, you as a user can disable it if you want to. I did it myself, and I was impressed by how many websites still work if I disable. Well, actually, I didn't encounter a single website that didn't work anymore by disabling third-party cookies. So if you're security and privacy conscious, you should definitely consider disabling third-party cookies in your browser. So this brings me to the conclusion. So we've presented HEIST, which is a collection of techniques and methods that can be used to reveal the response size of a resource as it was sent over the network. And what's most important about it is that it can do so in the browser. So any malicious JavaScript can use these HEIST methods. So the techniques are based on certain side channels, which originated from the rather subtle interplay between the browser level and the network level, so with the browser APIs and the TCP. And as a result of these side channels and the methods that can be used, it becomes possible to launch compression-based and size-exposing attacks. We've also shown that websites that are using HTTP2 are actually more easy to exploit. So that's quite interesting, I think. And in the end, I briefly touched upon the countermeasures and mentioned that although there are a lot of possibilities, basically only disabling third-party cookies is a good and complete prevention. So that concludes the talk. now we'll be happy to take your questions.
Hey guys. Hello. Hi. If the demo was actually working, what's the usual time to extract a CSRF token? How long does it normally take under normal conditions?
We actually have a video that I made last night, so
Yeah, we can show the video now where it works properly. So generally, we tested this also using a CSRF token of around 16 characters, where each character had 2 times 26 the possibility. So it was a very large CSRF token. But in our case, we were able to recover it in about 2.5 minutes. So it's rather fast, in my opinion.
And one last question. Is the demo against HTTP 1 or 2? And is it practical against both?
The demo is against HTTP 1. We did not implement a fully completed code for HTTP 2, but we did test it that against HTTP 2 it should work as well.
Thank you.
Hey. Hello? There was a paper earlier this year about breach attacks where the authors recommended first-party only cookies as a mitigation. Have you looked into that? Like, that's a new draft to set additional value to cookies, that the cookie will not be sent if the request comes from another site, as far as I understand?
Yeah, do you mean same-site cookies?
Yeah.
If that's implemented correctly, then that would also be a prevention against these types of things. So basically, if the cookie does not get sent along to elicit requests, then the attack will be prevented.
You're using the web performance APIs, but strictly speaking, that would just be to improve the speed of the attack, right? Otherwise, you can just use standard JavaScript date APIs and a lot more samples.
Could you repeat the question?
So you're using the web resource APIs or the timing APIs. Strictly speaking, that's just a performance optimization, though, right? You could just use standard date APIs and more samples.
Yeah. I think for the fetch API there, it is required to use that one because I don't know of any other API that returns the time, that allows you to execute JavaScript as soon as a response when the first byte was in. But for the resource timing API, this could basically be replaced by any other thing that allows you to determine when the response was completely downloaded. So the resource timing API gives a very accurate measurement, so that's why we decided to use that.
Yeah. Okay.
Can you clarify something for me? So you're able to send cross-site requests, and then determine the size indirectly by the timing, but you're not able to read the response. Why does the browser let you send the request in the first place if it's not going to let you read the response? Could that be used as mediation? Just disable the cross-site request in the first place?
But the thing is that if you go to, for instance, New York Times, then a lot of cross-site requests will already be sent. So if it includes a JavaScript library from a third-party domain, then that will send out third-party requests. So the web is, I think, built on the fact that you can include content from other origins. So I think that's something that will not likely go away in the near future.
So if you have the same character twice in your CSRF challenge, how are you determining the position of that same character when it shows up again a second time?
Because that is basically the breach attack. So For your first, let's say you have the character K. The first time this K occurs, you're trying all other characters, but you find that the K is included into the back reference of the gzip compression, and it results in a smaller reply. Then if you try the second K, you have exactly the same story. If you would try another character, this would not be included in the back reference that is used during this gzip compression, which removes repeated occurrences. But if you use the second K again, then you have both Ks that are included in the back reference, and then you again have a shorter reply. So if you have Ka, for example, compared to Kk, then Kk will be shorter than Ka. So it's basically the breach attack.
Okay, and that holds also if you do a KAK or a KABK.
That would all just work fine.
Cool, thank you.
Yeah, you can use the microphone over there.
Were those two different types of mitigations that you mentioned regarding cookies that both work? One was disabling third-party cookies, and was there another one that was separate from that? I could use a clarification.
It's a standard that is very new, so I think only a month or two old. It's called same-site cookies. So it's you already have the HTTP-only cookies and secure cookies. So HTTP-only cookies cannot be accessed from JavaScript. And with the same-site attribute, you can prevent cookies from being sent when the request is of a cross-origin nature.
And how does that differ from how disabling third-party cookies mitigate this vulnerability?
So third-party cookies will prevent all third-party requests from containing cookies, whereas with the same-site cookies, that's an opt-in from the website. So it needs to be, the attributes should be there in the cookie, otherwise it will not be applied. Okay, so I think we don't have...
One last question.
So you were saying that the turning off compression was only a partial mitigation? Why was that?
Because then we can still, if we turn off compression, we wouldn't be able to directly apply the breach attack, but we still would be able to determine the exact size of certain resources, which is still sensitive information. For example, we could determine whether a person was logged into a particular website or not, or you could visit certain profile information and then even uniquely identify a person purely based on certain resource sizes.
I don't think we have time left for questions, so if you have questions...
Yeah, we can take it offline. Don't worry.
Yep.
Thank you.